Okay, up here is some pertinent dates to pay attention to. They're also on the checklist we teach you all. I put them in this morning. The amine nomenclature quiz will be due by midnight next Monday. We'll finish up nomenclature today. We'll be starting that. And then I just want to call your attention largely to this right here. This is the Monday after spring break. The Wednesday after spring break, you have your exam. And I'm going to move it into lab because there's the lab, we can do the part we need to for the lab in a half a day and then finish it up the next day. But in lab, I can give you a little bit more time because analyzing C13 and analyzing mass spec, it takes some time. And so it's better to give you a little bit more time to work on stuff. So we'll probably do an hour and 40 minutes for the exam or so. It gives you an extra 20 minutes. And then we don't have the class that comes in like right on the dot, shoving us out of here. So we're going to move the exam to lab. The day before that, which is Monday, the class before that, you have a lot of stuff due. And so I wanted just to kind of draw your attention to that and warn you to space it out. These are like the absolute last deadlines for some of these things. You have two synthesis worksheets. One's pretty straightforward. The other one is a little bit harder. And they cover two different kinds of amine synthesis. Both of those will be due, and we'll go over probably a selection in lab. We don't have time to do every single one. So let's make an executive decision on this. How about you turn in the odds, and we will cover the evens in lab.
For both worksheets?
For both worksheets. Otherwise, we're going to spend the whole lab time doing worksheets. I don't want to do that. So you guys turn in the odds, and we'll cover the evens. And you can remind me of that later. That'll be due Monday. Also, Monday at midnight is the absolute last time to take both the C13 and the mass spec quizzes. You might not want to wait until Monday at midnight, because then it's real hard to ask me questions if you have any. But that is the absolute last time to take those. And so it gives you a lot of time, and spring break is in there, but just pay attention to that and don't let it get piled up on you at the last minute. Okay. What we had finished up with last time, I think we were somewhere in the middle of this matching exercise, and I don't think we've gotten very far into it, have we? Did we decide what the first one was?
We decided it was either D or F.
Turn some lights off. There. See a little bit better. So that first one, you can see that there's a carbonyl, and it's out above 200. And we have a number of possible things that have carbonyls in them. We have an ester, carboxylic acid, and a ketone, right? Taking a look at that list that you guys have of where the absorbances occur, if you take a look at carboxylic acids and esters, they show up around the 180s, and they're a little bit lower. So that right there is sort of pointing to it being a ketone. So thinking it's this right here. Then it should have some C double bond C's in it. And those show up at around between 100 and 150. And there they are. Right there. So this first one, I think we decided on this last time, was D. Okay. The next one. I see a bunch of alkyl stuff. That in itself is not the most helpful thing, but you can see down here we have some CH3, but everything has that, so not too helpful. What do you see right there? Where is that roughly? Yeah, it's about 170 or so. So that is probably the C double bond O of an ester or carboxylic acid. So we're looking at F or G. So how are we going to make the decision between those two, between F or G? Yeah, the benzene ring. that should show up with some peaks around where? Where does benzene show up? If you take a look, it's pretty wide range, between 100 and 150. It's pretty wide. Even can go up to as far as 160 if there's something electronic drawing there. So we definitely have some peaks there in that area. But what did you notice about those? Yeah, they're all going to be singlets because it's decoupled. So that we're not going to be showing any splitting. There's just two of them, right? And are there just two types of carbon in this?
No.
No, there's one type right there. These two are the same, but these two are different, and that one's different. There would be four types of carbon that were different. Here, 1, 2. So this one, the second one, is F. Second one is F. All right. One thing, if you get stuck on a test, I tend to look first for carbonyls or for some, really obvious functional group. And then one thing that can help you is to count the numbers of different kinds of carbons and then count up the lines. So, for example, the first thing I would do if I were tackling the second one is I'd say, okay, I probably have a carbonyl, and then cross out everything else. Then I would say I have 1, 2, 3, 4, 5, 6 different kinds of carbon. And I'd start counting. Here's 1, 2, 3, 4, 5, 6, 7. Uh-oh, what happened?
Two of them are the same.
Yeah, two of them had to be the same. And this one, I have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I don't have enough lines for that. This one here, what kind of functional group would you expect is in this? Just based on this peak right here. It's sort of a standout right here. And it's between, looking at this thing, can't even read this. It's about 75 or so, 78, thereabouts. Yeah, it's a carbon connected to something pretty electron withdrawing. And if you take a look, it's not a C triple bond C because we don't have that choice. Probably a carbon on an OH. So it's got something electronegative on it. So the carbon next to an oxygen. So could be this guy, could be C, or could be E. Right? And or it could be A. It could be A as well. All right. So what are we going to do to narrow it down from that?
Can you use the number of different carbons?
You can use a number of different carbons. Okay. So one thing that makes me kind of steer clear of E, going to the number of different carbons, is I have a number of carbons that would be almost equally de-shielded because they're right next to an oxygen, but they're different. So I would have this carbon here, right? That's going to be de-shielded next to an oxygen. That carbon there should be really de-shielded, and then that carbon right there. So I would expect to see 3 types of carbons down there, and I do not see 3 different kinds. So I'm thinking that probably not E. Okay. So count the number of different kinds of carbon here. 1, 2, 3, 4. Same over there. So 4 different types of carbon. And what do we have here? 1. This is kind of weird looking. 2, 3, 4. What's going on right there? See how it's split into sort of a very, very close little, like a doublet almost? It looks like there are 2 peaks there. That's a result of this being a chiral center. And you guys have probably done your reading. We haven't talked about this at all. It's like an advanced topic. The word diastereotopic protons. Do you remember reading about that? Vaguely? Yeah. What that when you have a chiral center, that means that that carbon is not the same in the environment is not the same on one side or the other. And the neighboring groups can tend to pick that up. Okay, so That's what's going on there. But I have narrowed it down to A or C. Is it C?
No. It can't be.
It can't be, there's no benzene. It has to be A. It has to be A. Yes?
Is the diastereotypical place for the first one, is that why there's like 8 lines instead of for the 7?
For the very first one, what we said that was D, and there's no chiral center there. So the reason, were there 8 lines in this when you counted it? Let's see, 1, 2, 3, 4, 5, 6, 7, 8. The reason there's 8 is cis and trans on that CH3. Makes them different. Okay, let's go to the next one. All right. What's the first thing your eye goes to on this spectrum?
Benzene.
Stuff right there. Benzene ring. So we're looking at either C or G. Can it be G? You think it's G? I don't see a C double bond O in there, really. There should be something around 180, and there's just not. The highest thing I have is below 140. And so I don't see that C double bond O. So process of elimination, I'd say it's that guy right there. If we count up the numbers of carbons, and let's ignore the benzene because that's just a crazy mess. Count up everything else. 1, 2, 3, 4, 5. I should have 5 lines that aren't benzene. Is that the case? 1, 2, 3, 4, 5 lines that aren't benzene. So this one right here, this top one, is C. All right. I wish I could write on there and scratch out the ones we've used. This next one,
B.
it's got a lot of different carbons in it. So, looking at the next one, do I have a carbonyl?
No.
No. So I know what it's not. Is it just, could it be B, just an alkane?
No.
No, how come?
Because there's only 4 hexacarbons in that alkane, and there's one more than 4.
Yeah, the numbers of lines isn't quite right. B would only have, these are the same, so that's 1, 2, 3, it have 4 lines. I got way more than 4 lines. Plus, I have some being deshielded. Right, that peak around 100 is very deshielded. And so I know it's not B. Do you see evidence of, there's no carbonyl. We already used C, so we know it's not that, but there is no benzene.
I see evidence of
What do you think?
ether.
Yeah, that guy right there. So, I have some crazy deshielded carbon at around 100. That has got to be the one right there in the middle. It's got to be that one. So let's count up the different kinds of carbons in this. I have 1, 2, 3, 4, 5, 6. There should be 7 lines. Are we good? Yep.
Yep.
So that second one is E. Is one really deshielded carbon. Next one down. What's that third one down?
B.
There's nothing much on it that is causing anything to be deshielded. So I can eliminate everything in there pretty much. I have no carbonyls. I know I have no carbons next to oxygens. It has to be B. And B would have 1, 2, the CH3s are equivalent, so 1, 2, 3, 4 lines right there. So that one is B. And the last mess, which is truly a mess. What do you think it is?
G.
It's G. Pretty much because we used up everything else, right?
No.
Okay. But let's say that, let's say I gave you, which sometimes I do, 10 structures and 4 spectra. Okay? So you can't use the process of elimination quite as well there. What would you notice about this one?
Benzene ring.
Has a benzene ring. Okay, so we can cross out everything else.
A carboxylic
It
acid.
has a carboxylic acid, and so we know right away we're at this. And then if you count up the numbers of carbons, let's not count the benzene because it's that crazy mess. I have 1, 2, 3, 4. I should have 4 alkyl carbons in the alkyl range. And if I come down, wow, 1, 2, 3, 4, I do. Okay? I have a carbonyl. I have the benzene. What is this thing? The one in between the carbonyl and the benzene.
Got the carbon on the carboxylic
It's
acid.
the one being shielded by the carboxylic
It's
acid.
that one on the ring being shielded by the carboxylic acid. It pulled it out a little bit.
It's not the C, like right under the double bond, it's the
No.
one on the benzene.
It's the one on the benzene ring, so it's that one right there. Too much coffee.
Too close.
It's that one right there. Okay. Any questions about C13 before we move to amines? Yeah.
How come some of the lines show up, like very dark lines doesn't mean that there's two overlapping or anything
No,
like that?
that one it doesn't, and I don't know why. This one it's computer generated, and it's on the bottom one, the one I'm looking at does not show up with those dark lines. So I think it's just a cut and paste thing.
Okay.
If you guys want to get some extra practice with this, on ChemDraw in the hallway, you can draw structures, just whatever you want. And then you can circle the structure, and you can go to, I think it's under structure, and it says C13 NMR. You know where you did the proton NMR? ChemDraw will also do C13 for you. And that's a way you might want to just like draw 10 molecules and see if you can kind of predict where things are. It's good practice.
Mass spec.
What's that?
Will it do mass spec?
It does mass spec, but in a weird way. Mass spec is looking at masses of fragments. So you can draw a molecule, but then in ChemDraw, what you do is you draw a line chopping off a piece, and it gives you the mass of that fragment. So it won't give you the mass spec and let you interpret it. It's not quite that good. Okay, let's go ahead then and start amines. And we'll be switching in between the board and the overhead. There, that's good enough. All right. Amines, you guys have heard of a lot of compounds that contain amines in them. They are very biologically important compounds, like dopamine. You've probably heard about that in the news, and epinephrine in the news. Epinephrine, you guys heard about that?
It's a brain
Yeah.
chemical.
Yeah, it's a bad chemical.
It's a brain.
A brain chemical, yeah. A lot of these are brain chemicals. Here's one. If you ever have intestinal worms, piperazine will kill them for you. What are some others? Histamine, which dilates blood vessels. There are some others I don't have up there. There's cadaverine. Guess what cadaverine does? Yeah, it's cadaver smell. So it's like the dead smell is cadaverine. And putrescine. What word do you hear there? Putrescine. Putrid, yeah, another rotten smell. Amines tend to not smell really good. The solids don't really have a smell, but the liquids tend to smell gross. They smell a lot of times like rotting fish. You get this rotting fish smell on you, or just putrid things. They are not pleasant smelling compounds, largely. Ammonia, you know, you think about ammonia's kind of urine-y sort of smell. They're smelling very biological, I guess. Okay. Now, we're going to be talking about amines in terms of 3 classes. And the first class that we are, and you know what I'm going to do? Let's try something. Normally I shine this on the board and write on it, which I cannot do. So we're going to do something I almost never do. I'm going to give you the answers. You can see them. There you go. Okay. So an amine that has just one alkyl group on it, so it's an NH2 with an alkyl group, is called a primary amine. If the amine, the nitrogen, has 2 R groups on it, it's a secondary, and if it has 3, it's a tertiary. Now, as far as naming amines. They have a common nomenclature system which works for ones that are really simple. And then they have IUPAC. IUPAC is a little different for primary versus secondary or tertiary. But once you learn primary, doing secondary and tertiary is pretty easy. So in terms of a primary amine, a simple, or just a simple plain amine that is not highly branched, no other functional groups in it, it's just the alkyl group and the word amine as one word. So that first one, there's a butyl group on the NH2, butyl amine.
Nice.
Okay, and then the next one, there's a sec-butyl group, sec-butyl amine. And then I threw that one in there because you don't name it as a, what it'd be like a 2-methyl-5-nitrophenylamine. You have to remember that that unit, the benzene in the NH2, has a name. It's called aniline. You gotta remember that. This is going to fall apart, however, when you get things that are a little bit more complicated. So when you start getting double bonds in there, or other substituents in there, that kind of thing. So as far as IUPAC goes, the way that I deal with amines is I pretend I am naming an alcohol. Everyone's very comfortable naming alcohol. You guys can do it yourself at this point. So pretend you're naming an alcohol. So for example, this guy right here, we called that sec-butylamine was its common name, right? But let's say you forgot that and you had to name it IUPAC. If it were this, and you were doing the IUPAC name of the alcohol, how would you name this?
2-butanol.
You'd have 2-butanol, or butan, 2-ol. Right? You can get away with either one of those. All you have to do is name it like it's an alcohol, and then instead of OL, put amine in its place. It is really that hard. 2-butanamine or butan-2-amine. So if you put your thumb over it, pretend it's an OH, and that's how you name it. So this next one, and I'm just going to redraw this thing real fast. This and that with ER. The nitrogen has priority over any of those substituents that are on there. And so we're going to start our numbering here. 1, 2, 4. If it were an alcohol, you would have it as butan-1-ol, if this were an alcohol, with all that stuff on it. So the parent is going to be butan-1-amine. And then you just put the substituents on. So the bromo's at 3. So we have 3 bromo, 2 methyl, butan-1-amine.
Yeah, that's right.
You got to put the 1, because otherwise, even like say with an alcohol, would you take this and name it butanol? Could you get away with that?
No.
No, you need to know where the OH is, right? So you have to need a number. Same thing here. I need to know where the NH2 is, so I need a number. Okay? That next one, now we have a decision to make. Take a look at your priority list and see where NH2, or amines in general, end up relative to alkenes. So I need to know if this is an alkene or an amine. Who's higher, amines or alkenes? Amines. Okay, so the amine is the winner, and I'm going to number this thing so that the NH2 has the lowest number, because it was the functional group that won. So I'm going to start over here. 1, 2, 3. The double bonds at 4, 5, and 6. So I have 5 methyl. The whole thing is a hex. It's really a hexene. So I have hex, 4-ene, and then 3-amine. Yeah.
Do you mind doing that problem with, let's say, an extra amine group on the same carbon, just so I can make sure I write it down?
An extra amine on the same carbon?
Yeah.
So something like this?
Yeah.
Okay, let's 2, 3, 4, 5. So it'd be 4-methyl. Pent. Be pentamine, but I'm going to go pentan 1,1-diamine. Just like if it were a diol, just a diamine. That'd be a pretty unusual compound.
You don't drop the N or, there's something about that, I'm forgetting.
Oh, you know, yeah, since there's a D, it would have that there.
Pentane.
Pentane diamine. Okay, so primaries are not bad. You just have to remember that the nomenclature it's exactly analogous to an alcohol. You're just changing the amine from ol to amine. But then we get to something a little more interesting. Secondary and tertiary amines. The challenging thing about them is that your nitrogen now has another group on it. This was not something we ran into with alcohols, but you have an R group. And let's say it's a secondary, and your nitrogen, and then another R group. So that's a little bit weird. And so the way that you do it, one of them has to be the parent. You have to select a group to be the parent. And typically, you pick the one with the most atoms in it, the longest chain. Or if you have an alkyl group that has a double bond in it, and it has a lot of branches, and it has this and that, that would be your parent. And you try to keep the R group here as a substituent, the simpler one. So one of them you have to designate a parent. And then what you do, once you've done that, life is easy. You're going to take it and you're going to name it as a primary amine. So I'm going to name my parent as a primary amine. And the other R group on the nitrogen, which is the substituent, its name just goes piled in with all the other substituents. Only, the substituents are like 3-bromo, 4-methyl, 5-chloro, whatever. They have numbers. But the other R group on the nitrogen is not on the chain. So I have to show that it's on the nitrogen. And so they use, instead of a number, a big capital N to show that it's on the nitrogen. So, looking at this example right here, I have to choose a parent for the amine, and I'm going to choose the cyclohexane as part of the parent chain because it's bigger than ethyl. So the parent is actually this guy, right here, the nitrogen in the cyclohexane. So it's a cyclohexanamine. Off of the nitrogen is an ethyl. So it's N-ethyl cyclohexanamine. Okay, getting something a little more complicated, I have a tertiary amine. This tertiary amine has a methyl, that's probably not the parent, an ethyl, not the choice, and then this thing. The thing is clearly the most complicated. I do not want to name this as a methylamine parent and have to deal with that as a substituent. I just don't want to go there. So this is going to be the parent. And then I have a substituent that's a methyl and a substituent that's an ethyl. So, numbering the parent chain, we will start where the amine is because it has the highest priority now. So we'll start right there, that's number 1. And then we have 2. And then we have 3. So the parent chain is 3 carbons long. Okay? As substituents go, I have a methoxy, a methyl, an ethyl, and another methyl. And what they will do is, since I have a methyl on the chain and a methyl on the nitrogen, we're gonna group those methyls together and call it a dimethyl. And the number that it gets is the number of the chain and the N. So when you have the substituents, they're alphabetical as usual, ethyls first, so it's N-ethyl. And then on the chain is where the methoxy is. It's at number 1 on the chain, so 1-methoxy. Then my methyls are in both places. So I go number 2 on the chain, and then at the nitrogen, I have dimethyl. And then propan 1-amine. Yes?
It's always the number before the.
No, it varies, actually. I don't care which one you put first. Some books you'll see N, 2. Some books you'll see 2, N. I don't know that it matters.
So anytime like the substituent is on the N, you should like put N, right?
Right, anytime that substituent is on the nitrogen, put N. Yep. Yeah,
And the N comes before any number, right?
no, it doesn't matter. It doesn't, you'll see it either way. Okay? Yes? The N is, no, it's never lowercase, it's always capital. Yeah, it's always going to be capital. All right. Now, take a look at your priority sheet again. And tell me, compared to, say, an aldehyde or a ketone, where do amines end up? They're lower. So guess what happens if you have, let's say, a ketone in your molecule and a nitrogen? If that molecule is a ketone, if it is named as a ketone, that NH2 loses, it has become a substituent, and as substituents, it is an amino group. So this is just named as a cyclohexanone, 3-amino, 5-isopropyl cyclohexanone. So when you have a higher functional group, it wins and your nitrogen becomes an amino. Yes?
What if it was like secondary or tertiary?
Okay. I think, let's see, are we going to deal, let's go ahead and we'll draw one up. Brian's question is, what if that nitrogen is substituted? What do you do then? So, let's go ahead and draw one up. Let's say I had this, and let's put a bromine there, and let's put it in CH2CH3. Something like that, right? Is that what you're asking? Okay. So it still is going to be a cyclohexanone, and numbering wise, that'll be 1, that'll be 2, 3, 4, 5. Okay. So it's 5-bromo. I think I've got my alphabetizing right, we'll check in a minute. And then 2, and then go into parentheses, because now it's going to be a complex substituent. And you can do one of two things here. You can go ethyl, amino, or N-ethyl, amino, cyclohexanone. That's how they deal with it. It just becomes an ethyl amino, or you can go N-ethyl, N-methyl amino, like that. Yes?
So if there's a carboxylic acid on the alkyl chain on the right, then you name the thing
you
as
would
substituent?
not be a happy individual if that were the case. If there were,
This 3 groups now.
like that,
Yeah.
oh, yuck. What just happened to you, this is now the parent.
Okay.
That's the parent. And so you have your carboxylic acid name, in this case it would be propanoic acid. And then you would have at number 3 of this propanoic acid,
It's huge substituent.
a mess. Yeah.
Carboxylic.
Wow. You would have N dash, you probably need brackets for this actually like that. N dash, and then in parentheses,
Do you?
wow, how would you even do this? 1, 2, no, 1, probably 1, 2, 3, 4, 5, 6. starting to guess here now.
Four
So,
bromo.
4 bromo,
4 bromo.
maybe 2 oxo,
2 oxo.
cyclohexyl, close that down, amino, put that bracket there, propanoic acid.
Yeah, no.
You won't do this to us, right?
No. I'm kind of guessing on the 2 oxo part, I think that's probably right.
I think
But that's my nearest guess as to what you have to do with that. Not pretty, but that's how you deal with it. Not unlikely to do that. It's too hard to grade. Okay? That's nomenclature. It really isn't too bad if you just remember to name it like an alcohol. Now, in terms of properties of amines, the nitrogen has 3 groups on it and a lone pair. And so we want to be able to get all of those electrons as far apart as possible. And so what you end up seeing is that the nitrogen is sp3 hybridized, and the electrons are then in a tetrahedral sort of geometry. So this is just the electron geometry, something like that. And that's showing the 3 bonding pairs, the bonds, and then the lone pair. So when you put groups in, let's just put a couple groups in. We have a lone pair up there. Put a CH3 here, and I don't know, an H there, and a CH3. You can't see the lone pair. It doesn't contribute to anything visually in the molecular geometry. So what I can do, in terms of what the molecule looks like, write that out. So what you're looking at is what kind of geometry? Trigonal?
Pyramidal.
Pyramidal, good. Trigonal, pyramidal geometry. And that kind of makes it interesting. We're going to go back to one of your favorite topics ever, and I'm going to show you guys something. You'll know what the topic is when I draw this. I'm going to put I'm going to switch this out. I'm going to put 3 different groups on there. Let's put an ethyl group here. I didn't want 2 of the same group for a reason you'll see in a minute. I'm going to draw a mirror.
Come on. Why are you doing this?
So where am I going with this?
Chemistry.
So draw the mirror image. So N, yeah, no, H. It's my favorite topic too, trust.
That's the one that made you throw a book against a wall?
This is where I cried, yeah.
Yeah.
For those of you guys who have not had me in class before, stereoisomers made me cry, like really hard when I got to it, and I was in your shows. I hated stereoisomers with a passion. Okay, so this is the mirror image. Now, here comes the hard part for me. Take it and turn it and see if you can superimpose it on this guy.
It doesn't.
It doesn't, right? So I turn it, I can get the CH3 to match up, but the minute I do that, the ethyl's forward and the hydrogen's back, right? So this is a non-superimposable mirror image. There's a special word for that. What's the relationship of these 2? They're enantiomers. They are enantiomers. So amines that have 3 different groups on them are chiral. And so you can actually see, when you pick up a bottle, you'll actually see if the amine is correctly arranged, an R or an S in front of it, and that's why, because they are actually chiral. Now, one of the interesting things about the 2 amines is that they interconvert rapidly through something called an umbrella conversion. umbrella inversion is exactly what it sounds like. You know when you take an umbrella out in the wind and it flips like from the way it's supposed to be to up? You know, you've seen people like that, all of a sudden that's an umbrella inversion. So what's going on is picture the amine down as an umbrella like how it should be. And what happens in an umbrella inversion, let's just go umbrella invert this guy. In the umbrella inversion, this group's going to go up, that group's going to go up, and that group's going to go up. So it looks like this. CH3, and then the H is now up, and the ethyl is back up.
That's the same.
Okay, so it's just inverted. And now here comes the fun.
It's the exact same as the one.
Take it, flip it down. Well, we flip it this way and come over. It is the same as this. You guys see that?
Yes.
Do you? Yeah. If you just take this and kind of just twist it like that, you can see it. This guy is the same as the first molecule. So what happens with amines, you can have an amine that is R. But if you put it in a bottle, it's doing this umbrella inversion. And so R is going to S. And then S is going to R. And you end up with a mixture.
So we don't need to do anything.
So you'll, on a lot of amines, you will not actually see. If I pick up like a liquid, if I were to pick up a bottle of this, it would not have a chirality indicated because in the bottle's both. Okay? In order to isolate one pure chiral amine, in order to get a pure enantiomer that is not inverting, I have to stop the inversion. That's the only way that I can hopefully, or hope to isolate, say, an R or an S, and not have it constantly going back and forth, R and S, through this inversion thing. So, to stop the inversion, what are some things you think you should do?
React with something.
React it with something? Okay. That is one of the things they do. You can take, and let's say you have this chiral amine right here. I have an H, and let's just say I have an ethyl and a propyl group right there. You can protonate it. When I protonate it, I have an H there. It has a plus charge. The minute I have done that, I can't do the inversion anymore. The inversion requires, at some point in time here, in this inversion, I have to have this. I have to have trigonal planar geometry. I must pass through that. If I'm like this, and then it goes like that, at some point it's like this, right? So it's trigonal planar. Trigonal planar geometry is sp2. So it's passing through this sp2 momentary hybrid situation. With the thing protonated, there is no lone pair. sp2 is not possible. It can't invert. It's stuck. So one thing they'll do is they will protonate it and make it a salt. And that's where, if you go in the stockroom and pick up our solid amines, some of them have R or S on them because they're not sitting in there doing this. They are locked. They're locked in place. The minute you deprotonate it, it's over with. But protonated, they're stuck. What's the other thing you can do?
Could you force a double bond on there?
Kind of like that. What you do is you put it in a structure where it can't invert. And the typical way of doing that is not to put it so much in a double bond, but put it in a ring that can't convert, like something like this. What if I did, so, draw this right here, I got weird. Why can I not, there we go. What if I and I put, I don't know, a methyl, there we go. There's my 3 different things on it. Now, 3 different things on it. And here, this bridge can't invert. So you can put the amine into a ring, which can't invert. So that bridge is pretty clearly not going to go flying through the center of the molecule back down to the bottom. That is not going to happen. So it's stuck. So what you see there is you see bridges. Put it in a bridge, or put it into a small ring that can't do sp2 bond angles. Because that's 120 degrees, right? Big rings could. It's high energy, but they could. It's very common if you put an amine into a 3-membered ring like that, and let's put some groups on there. There's a carbon, a carbon, and a carbon. That 3-membered ring is 60-degree bond angles. There's no way that it's going to be able to stretch out to 120 all of a sudden. It's too highly strained. So you see it in really small rings. And the example that's always given is 3-membered rings. Okay? Yes?
It doesn't seem like you can actually use the amine as you want to, like in a reaction. Why would you like go through all the trouble to do that?
If you just wanted to build it, let's say you
Just
wanted
wanted
to
to
build
see
that amine. You're right, the reaction is not useful because the lone pair attacks something.
Yeah.
It's a positive charge, and I have no way of deprotonating it, right? So it could be, and I could have stuck a hydrogen here, I guess, and had done things with it. But usually, you're building an amine as kind of your end product.
Okay.
Yeah, Ryan.
For protonating the amine, doesn't it lose its chirality once it's protonated?
Once it is, well, let's see, what if I had, this is probably a poor example of this. What if I had changed that to a CH3? Because that's a good point. Yeah, you have to start out with something that would be chiral before you did it. The last thing, this is kind of a sleazy trick, this last thing that you can do. Let's say I gave you an amine, and I told you that it was R now let's not even do that. I'm just going to draw a smart name. Picture is worth 1,000 words. There's a nitrogen. Here is an ethyl. Here is a methyl. And here is chlorine and hydrogen. The nitrogen part of this has nothing on it to keep it from inverting. It's not protonated, it's not part of a small ring, it's not part of a bridge. So this guy is inverting. So it has an indeterminate stereochemistry. But on the bottle, whatever this thing's name is, you would still see S. And then whatever its name was. Why would you see that? It would have a chirality indicated, even though the nitrogen's inverting like crazy. Yeah, the chirality on a bottle that you read the name does not necessarily have to come from the nitrogen, right? You can have an amine, and on one of the alkyl groups, the chirality could be coming from a chiral center somewhere else. Okay. So that is all about enantiomers and how those guys. In terms of solubility and odor, the odor we kind of already talked about. It's nasty. But in terms of solubility, all amines, whether they are primary, secondary, or tertiary, can accept hydrogen bonds from water and from alcohols. And these guys, they're all acceptors. And these two right here are also donors. They're hydrogen bond donors as well. And so what you see is that their amines do have, well, some water solubility. If they're small, like they have less than 6 carbons, they're soluble in water. If they get bigger than that, they start to get more alkyl-like and less amine-like, and then they start to lose water solubility. If you have branching, that tends to increase solubility. It makes the molecule have a smaller surface area. Most amines smell really bad. Smell like rotting fish. So there it is. There's cadaverine right there. It's a diamine. I wonder about the person who smelled dead people and said, I think I'll isolate that smell. You gotta wonder about that. Whatever. As far as the boiling points go, we're going to see typical trends that are in line with their ability to hydrogen bond. Remember, with the boiling point now, we're not talking about dissolving in something else. So with the boiling point, it really is what kind of bonds can, for example, primary amine form with other molecules just like it? What kind of intermolecular attractions? So what we see, there's weaker hydrogen bonding. Tertiary amines cannot hydrogen bond to themselves. And they can accept from water, but a tertiary amine and another tertiary amine cannot hydrogen bond together. So what you see is boiling points that kind of reflect that. The alcohol, which is the very top one, is propanol, boils at 97 degrees. It's really high. And because it's polar, it can hydrogen bond. The corresponding amine drops down to 48. So it's still high, but it's not nearly as high. And the only thing I did was switch out a nitrogen for an oxygen. That amine, the second one on the list, it can donate hydrogen bonds to another amine. It can accept hydrogen bonds. But it's lower boiling point because it has weaker hydrogen bonding. If you remember that hydrogen bonding relied on a hydrogen attached to a small highly electronegative atom, right? So the hydrogen had a really big delta plus, oxygen had a really big delta minus. And it was the attraction for these electrons around the oxygen that gave really good hydrogen bonding. Looking at nitrogen, nitrogen's less electronegative. It's not pulling electrons quite as much towards itself. So the delta plus here is a little smaller. It's not quite as electron starved. The delta minus on the nitrogen is also smaller. So you don't have a nitrogen with as much electron density, and you don't have a hydrogen that is as electron poor. And so the interaction is just weaker, so you don't see the high boiling points. They're still high, just not as high as an alcohol. And then that poor tertiary amine, it has nothing, and so it's down at 3.5. It's a really low boiling. Okay, this next thing, if we have time, we'll talk about it at the end. We're not going to do it now. All right, so now for the fun. One thing amines do is they can function as bases. And so we need to spend a little time talking about their basicity. The classic one from your 400-401 experience is ammonia functioning as a base. With H+, we get NH4+. And what's going on there is the lone pair is attacking hydrogen. It does this more effectively than an oxygen would, much more effective. Why is it a better base than water, for example? So why is the corresponding not as basic because it's more electronegative. The oxygen is more electronegative, which means what? It holds its electrons tighter to itself. They aren't as available to go out and attack.
So it's not as much of an electron donor.
It's not as much of an electron donor, exactly. And since oxygen is more electronegative, this is not as favored in O+. Okay, oxygen is seriously not. That's not good. That's higher energy than an N+. It's not quite as bad. So you've seen that. You've seen ammonia as a base. You also have seen it as, let's just put this reaction up. See how well you do here. Let's say I wanted to make that. How am I going to do it? Okay, SOCl2, dionyl chloride, and pyridine, right? And we saw that mechanism last semester. Pyridine looks like this. It's a benzene ring with a nitrogen in it, essentially. And pyridine functions as a non-nucleophilic base. So in this reaction, if you sort of just balance it out, I am going to be generating, when all is said and done, there's an HCl somewhere that pops out of there. And the pyridine is going to react with that H+ and get rid of it. So when we have reactions where an H+ is being removed, oftentimes you'll have pyridine added in. And it stinks like fish. It's really yucky. But so that's two examples where you've seen the nitrogen functioning as base.
Where's the H+ being removed from? The
Oh, if you go through the mechanism, the first thing that happens is this oxygen here attacks the sulfur, and when it does that, it develops an OH+, and you have to get rid of it. So pyridine does that. Okay, now I'm going to give you guys some pKb values. We'll work in pKbs for just a minute since these are functioning as bases. Here we go. We'll do NH3, and then we'll do an alkyl group on there, an ethyl, NH2. Then we'll do 2 ethyls. And then we'll do 3. And these are pKb values. So here are the numbers. 4.74 for ammonia. And then 3.36. And then another one. And then 3.24. So write down the numbers and then we'll orient ourselves for just a minute. Because I'm sure about 3/4 of you are thinking of pKb now. How does that work? Right? Okay, so if I were giving you pKa values, say we're talking about carboxylic acids, and I give you pKa values, if I have a small pKa, the number's smaller, is it more or less acidic? More acidic, okay. So a small pKb is more basic. Okay, so what we're seeing here is that these numbers are all fairly small, right? And so these are all reasonably good bases. That's the first thing to notice. They're smallish numbers. So they're good bases. Then we see that the pKb value starts out with just plain ammonia, 4.74, and it is decreasing. So pKb is decreasing to here. What is that telling you about the base strength of the 1-ethyl and the 2-ethyl? What's happening? The 2 is more basic, the 1 is more basic than amine. So we have base strength increasing as we go that way to here. Something happened out there, and we'll talk about that in a minute. But looking at just those first 3, we're getting more and more basic. Okay, any ideas as to why?
carbons are electron donors.
Good, okay.
Is it inductive?
It's the inductive effect, yeah. These carbons are electron donors. And so by the inductive effect, they're pushing electron density towards the nitrogen. And that means the nitrogen has more electron density, and that makes it more basic. So you put one R group on, the nitrogen has more electron density. I put two R groups on, it's even better. I put three R groups on,
Sounds
it
so
should
good.
be fantastic, right? But it wasn't. So we've explained the first three, but completely fell apart on the last one. So there is something else going on. There is the inductive effect. But what else is happening is a deal with solvation. So when you're looking at base strength, you have two factors going on. Number one, the inductive effect. That helps explain why NH3 is not as good as a primary and not as good as a secondary. Primary and secondary. But what also is going on is solvation of the ion. So, with, this should be, this tertiary, by the inductive argument, it should be very basic. It should be the most basic. But it's not. And that's because when it grabs an H+, the molecule looks like this. It is highly hindered. So it's very hindered. I've got a lot of branching going on. And this ion is not existing in the gas phase. We're not doing gas phase chemistry here. There it's in solvent, right? And because it is so hindered, solvent is having a very hard time getting around it. Solvent has a hard time approaching and stabilizing it. And so it kind of going to three groups on there is sort of the breaking point. Yes, by the inductive effect, it should be great. But once you make the ion, if you can, you just can't stabilize it in the solution. And that ends up winning out over the inductive effect. So there's the solvation effect. Here, solvated secondary, it's not great, but it doesn't overcome the inductive effect. And tertiary solvation is just too poor, and so it's a little tougher to make that. All right, and that's a trend you guys will see, is that the amines pretty much increase in basicity, but tertiary is about the same, roughly, as a primary. Okay? Now here's another one for you. And let's just do it as, let's do it as two problems. I'm just going to put up two problems and see what you can do to advance them. Here's two other amines. And now, I'm going to torch you a little bit. I'm going to switch to pKas. I know.
It's funny.
You have to be able to handle both, because on those standardized tests that you're all going to be taking sometime in your life, they will throw both of those at you. They'll give you pKas of amines when they're functioning as bases, because everyone thinks in terms of pKas, and they may give you pKbs as well. So you have to be able to do both. The pKa is not that bad. It's sort of it's a mental gymnastics issue. So what we're looking at with pKas, let's let's just do a quick tutorial over here. These always sort of turn my brain around a little bit. Okay. So I have, with a pKa, here is my amine, and it is grabbing an H+, and it is forming the ammonium ion. Doing this, it makes sense to look at a pKa. The pKa is going backwards. So what we're looking at with the pKa is the protonated amine and its ability to function as an acid and lose the H+, to go back to the regular amine. That's what we're looking at with pKas. Okay? So, that being said, if I have a small pKa value, what can you tell me about the strength of the acid? Right, it's a strong conjugate acid. So if that amine is able to lose the H+ pretty easily, what does that tell you about its strength as a base? Yeah, it's not really hanging on to the H+. It's not that great of a base. So this means that the base is weaker. Okay, and its pKb would be high. So a small pKa, high pKb. And that's a relationship you saw in 400 as well. Okay, so when you see a pKa, what they're talking about is the reverse wheel. So here we go. Small pKa. So that's telling us that the conjugate acid is pretty good. So this is telling us that this is the weaker base, right? Does that make sense? The conjugate acid of this is not so acidic, so this must be a better base. I hate when they give me pKa values for these. I always
Question?
Yes.
When you say conjugate acid, is it, are you considering
That
that
would be-
as an H3?
That would be that guy, protonated. Okay, so this is a weaker base. How come?
Because electrons withdrawing from the electron.
Yeah, you're looking at, remember the lone pair? The lone pair here is dumped into the benzene ring. Okay? And here it's not, the lone pair is fully available. So, with that in mind, let's get to our problem. And let's see how this thing here is. Okay, I'm going to give you 3 compounds and 3 pKa values. You tell me which is which. Okay, there's 3 compounds. So here are some pKa values. And these are pKas.
Who wants to match them?
I want you to match them up for me. Tell me who's who.
Middle is 500.
And while you sit there and think right before you go through the answer, this is just a thought question for next time. All right. fundamentally get away from pKa's, because I can't deal with them. So, if the pK is 1, that's the strongest conjugate acid in the series. What's that telling you about the base?
It's very
Okay,
weak.
it's the worst base. And this one's going to be the best base. And that's the first step I have to make. I have to get away from pKa's. So, which one of these is going to be the worst base?
And that's
That one?
And
How come?
Because it's withdrawing from the over there
Okay, this is
and
a
it's the benzene.
huge electron withdrawing group. What's it going to do to this lone pair?
Just taking it.
It's going to suck it right into the ring. The ring is electron poor, and it has a nice lone pair that it can pull, and it's really delocalized. So this is the pKa of 1.0. Okay, so the next one, the middle one, let's leave because it's hard to do the middle one. Which one's going to be the best base?
The OCH3 on there.
Okay, how come?
It's got a donating lone pair that's been talked in.
Yeah, we saw when we were looking at directing effects that having an OH or an OCH3 on there could function as a donor, it was an activator, right? Did orthopara. So this is donating in. That means this is electron rich. And that means that this delocalization into the ring is much smaller. It's much less likely to occur. So this nitrogen has more electron density available. So this was the 5.34. This guy was 5.08. It's not quite as good of a base, right? Not quite as good, but it was still okay. What's going on with the CH3? It's an inductive donor, yeah. So it was inductively donating. That's a pretty wimpy effect. It's something, but it's not spectacular. Okay? That's your thought question right there. Think about it and come back with an answer.